speaker, which is a paper about the mobile gantry architecture by Professor Peter Staritz and the co-author. May I ask who is going to present? May I ask who is going to present for this second paper? Oh, hi. Hi, Professor Peter Staritz. Hi. So can you turn on? So you are on site or? Sorry, Jose. Have you seen Professor Peter?
No,
sorry,
I think
I'm remote. Okay. So Peter, can you share your screen, please? Okay. 1 second. Please. Oh, okay, great. Thank you very much.
Can you hear me?
Yes, perfect.
Great. All right, I'm ready when you are.
Yes, so may I introduce the second speaker, Professor Peter Staritz, who is presenting about the prototype of mobile gantry architecture, where they develop a railless gantry roll directly on the unprepared planetary surface, which is, I think, is a very interesting topic to discuss. Thank you very much. So, Professor Peter Staritz, the floor is yours.
Thank you so much. I very much appreciate the opportunity to speak with you this morning. I am going to be speaking on Mud Dauber, a prototype of the mobile gantry architecture. I'm from Taylor University, and again, my name is Dr. Peter Staritz. So let's go ahead and get right into it. Human beings are explorers, and for as long as we can remember, we've looked to new places to explore. And our next frontier is the solar system, or perhaps even beyond. If we are going to explore the solar system, though, there are better places to call our launching point than Earth. In fact, Mars is a much better place to use as a launching point to explore the rest of the solar system because of its very low gravity. It's much easier to get things off the surface of Mars than it is to get them off the surface of Earth. And so to make it a cost sustainable approach, it's useful to use Mars as our starting point. In the near term, we'll send astronauts to Mars, and we'll send habitats with them, places for them to live and work. But when we're talking about having self-sustaining colonies capable of being our launching point to the rest of the solar system, we really need enormous structures capable of holding hundreds or even thousands of astronauts. And so we need to construct those buildings there on the planet out of locally available resources. And so what we need are robots that can work independently, autonomously, and build much, much larger structures. And the advantage of building the structures out of in situ resources is that we'll have much larger volumes, superior radiation protection, and much lower cost. So in general, when we talk about autonomous robotic architectures for 3D printing, we talk about 3 basic types. There's the fixed base radial arm architecture, which prints from a fixed location. Often it will move between prints, but it is just a large arm that can print. The disadvantage of this architecture is that the size of the structure is directly proportional to the reach of the robot. And then because of this, structures are generally much smaller and often are independent because it's difficult to tie structures together without having the room to structurally bind them. The mobile robot architecture is another common approach. The idea here is that you have a swarm of many robots working together, printing and moving all at the same time to build a structure. This is the disadvantage of this is there's a significantly higher control complexity and much greater number of print discontinuities. And what I mean by this is that when the robot must roll and print at the same time, it has much harder time coordinating the motion of the arm and the body. In addition to that, it cannot always be printing. It must stop in order to reposition the robot. And those discontinuities in print weaken the printed structure. Also, the size of the robot determines the size of the internal structures in the building. So for example, if you have a robot that's 2 meters wide, then every opening, every hallway must be at least that wide to accommodate those robots. Finally, you have slower build times due to tetherless operation. The final type of architecture that's common is the gantry architecture. This one's very enticing. It has a robot running on rails. Unfortunately, the build size of the buildings that can be built must be encompassed within the robot itself. So the length, width, and height of the robot determine the length, width, and height of the building. Also, there is the problem of moving rails between prints, which would require additional robots in the Martian context. This team is developing the concept of the mobile gantry, which is a hybrid between the mobile robot and the gantry robot. And during the print, the mobile gantry rolls back and forth as though on virtual rails. But between prints, it's able to maneuver between sites using its wheels. The advantages of this are that the length of the buildings are not limited by the size of the robot. The control of the system is very simple and very low computational demand because it is always printing from above like a normal gantry. And it has very long continuous print paths, meaning, again, that it can extrude a continuous path on a single level before breaking that print to raise up to another level. And then it is capable of using the printed structure as scaffolding. This is a really exciting opportunity. You can see in the lower right-hand corner, what we do is we actually print the walls of the building at the distance of the wheelbase of the robot, and then we roll up on that structure in order to continue building higher and higher. And the advantage of this is that the structure can actually be taller than the robot itself. Looking in the upper right-hand corner of this image, you see 6 arrows, 3 blue and 3 red. And these illustrate sort of a key component of this architecture in that the blue arrows indicate the degrees of freedom in the robot that move the workspace of the robot. So it can roll back and forth. And then what we call the fine positioning system, those red degrees of freedom, can be moved left and right and up and down using what we call coarse positioning system. And then the very precise motion is performed using the red degrees of freedom. I'll explain this more in just a moment. So Dauber is a prototype of the mobile gantry robot. It is designed to explore what this design can do. And in the laboratory, our prototype is about 2.5 meters wide, 2 meters long, and about 1.5 meters tall. It has 4 major subsystems that we've been exploring: the coarse positioning, fine positioning, the printhead itself, and then the localization system. And this robot was developed as part of an undergraduate capstone program. So the coarse positioning system is really designed to do 2 things: position the workspace and perform terrain compensation. In our prototype in the lab, we have enabled x-axis or rolling mobility. And so it allows us to move back and forth and perform skid steering. The Y, Z, and turning axes have not been implemented, primarily for cost and scope control. What this means is that in the laboratory, we have a relatively confined workspace of only 30 centimeters wide, 30 centimeters tall, but we can print as far as we can roll in the lab, which in this case is about 1 meter. Clearly, we're not ready to build human scale structures, but this is a good way for us to explore the various capabilities of the architecture. We've also implemented terrain compensation. And the idea here is that we want to always keep the robot level despite the terrain or the fact that it may be climbing up on a structure. And so we enable the legs to extend and contract. And in this case, we have 1 leg extending and contracting, again, for scope and cost purposes, but it allows us to remain level while going over obstacles. The fine positioning system now is capable of following the exact print path that's necessary, regardless of what the workspace is doing. So it's isolating the motion of the print head from the motion of the robot as a whole. In this case, in the Dauber robot, it's an inverted XYZ platform, and this is sufficient to show the capability and the isolation. It gives us precise and simple positioning of the print head. And what we've done is we've made this an inverted gantry, or an inverted platform, excuse me, so that the lowest point on the positioning system is always the printhead. Unfortunately, because we've done this, we can't show one of the more exciting capabilities, which is this idea of self-scaffolding, and that will come in future research. I've shown there the print volume available, and the important part here is that even though this system is capable of printing at about 5 centimeters per second, and so when we consider the motion of the robot, we have a consistent 2.5 centimeters per second of print speed in the world frame, regardless of the motion of the base robot. The printhead system is capable of extruding sulfur concrete. We've chosen sulfur concrete because sulfur concrete is something that's going to be very easy to make on Mars. Sulfur is in abundance on Mars. And so sulfur concrete is a mixture of sulfur and sand. And what we do is we load up the hopper with the correct percentages, and we heat it to above 113 Celsius, which melts the sulfur. We then mix, the system mixes to ensure wetting and homogeneity, and then we can extrude. And as it extrudes, it cools and forms structures. And you can see some example structures there on the right-hand side. We have an 18 cubic centimeter per second volumetric extrusion rate. The printhead itself has 2 independently controlled heating zones so that we can precisely control the output temperature as it goes. Finally, I'd like to talk about the localization system. And the idea here is that we need a way to identify the exact positioning of the printhead as we print and isolate, or be able to know, despite, for example, wheel slip and stuff like that. So what we're using is a system that allows multilateration. We've got a total of 3 base stations and receivers on the robot, or the system will have receivers on the robot that measure the phase offset from the base stations versus a reference clock and allows us to measure the distance. The progress at this point is actually pretty early, and what we've got is a low precision distance measurement system, and again, a multilateration estimator. The final thing I'd like to say is that just in terrestrial applications, this architecture could actually have a significant impact. Current systems use rails, but the mobile gantry architecture has the potential to reduce the cost of setup and increase the size of structures. And in military context, the reduction of manpower required could save lives. Thank you so much. I did want to take one moment and just say thanks to the team that worked on this, and especially to the Indiana Space Grant Consortium for funding this work. I am finished. Are there any questions?
Thank you very much, Peter. So Jose, is there any question from the audience?
No.
In this case, maybe I will ask the first question. So I really appreciate your research about exploring this Gantry system, and in particular for the space architecture. So when you are doing the testing, do you have actually like a controlled environment which is mimicking the environment on Mars, or?
Yeah, that's an excellent question. So at this point, we are not controlling, for example, temperature and atmospheric conditions. No, so at this point, what we're really focusing on is getting the general architecture to work and basic functionality.
Thank you very much. So, and also on top, when you mentioned about the future research, so basically what you are currently working on, which is the scaffolding idea. So may I ask, how is the progress?
So we're actually making excellent progress. We've generated what we call the 2nd generation printhead, which is capable of continuous printing, and we're in the process of working on the new fine positioning system.
Thank you very much. That sounds very interesting. Great. So if there's no other questions, then thank you very much, Peter, for your presentation.